this one. So here we are in the week number 10, moment distribution methods. I think last week we talked about the slope deflection methods. If you have started doing your assignment questions, you probably know how to use these slope deflection methods. There are two only equations, that is the relationship between the internal moment and the slope and deflection. That is called slope deflection equation. That is a relationship between the moment and the slope and displacements. And when you have two far end is fixed, then you can use these equations. If your far end is roller or pin, you can use these equations. We have done lecture examples. We have done workshop examples where we have provided all these details. If you have a overhang, you can convert this overhang into the concentric moment, that is so on here, and that's concentric moment so on here. From these ones you can solve the indeterminate structures. If you remember the force methods, I think that force methods was quite challenging. And if it is degree of indeterminacy, degree of static indeterminacy equal to 1, the force method is quite convenient. No problem for us. But if the degree of indeterminacy become 2, it is a lot of displacement that we need to calculate. You need to use virtual work methods and it's a quite long. Then this slope deflection methods comes into the pictures and say that, OK, if you have degree of indeterminacy d equal to 2, well, d equal to 1, this is good. But when d equal to 2 is not good. The force methods not good meaning it requires a lot of work. And if it is more, then it is sometimes become impossible. Now, in the slope deflection methods, you can handle d equal to 2, state kinematic degree of indeterminacy d equal to 2, you can handle it. But if it is more than 2, then the simultaneous equations require 3 simultaneous equations to be solved. It is possible to solve 3 simultaneous equations, but it's quite challenging, and 4 almost impossible again. So in that case, the new methods coming is called moment distribution methods, where regardless of degree of indeterminacy, if the static degree of indeterminacy 3, 4, 5, you can solve this problem. Look at that progress that we are making. If you have degree of indeterminacy d equal to 1, force methods are quite useful, no problems. And it is still quite long because you need to calculate the displacement using the virtual work methods and so on. But it was quite doable. But in the slope deflection methods, last week we come across, I think degree of kinematic indeterminacy d equal to 2, we can solve it because there are 2 simultaneous equations. If it is only 1, then only is 1 simultaneous equation. If there are 2, then there are 2 simultaneous equations in trio. But now moment distribution method is quite powerful that you're going to do it. Now, as you know, I think from this week 1 to week 7, we have determinant structures. We have force methods that we introduce in the week number 8, which is the indeterminate structures. When degree of indeterminacy d equal to 1, it is good. Then degree of greater than 1, it is not good. Then we introduce slope deflection methods where degree of indeterminacy 1, 2, 3 sometimes possible because you have 3 simultaneous equations. But when it's 4, it is quite not possible. Then here moment distribution methods, you can do 1, 2, 3, 4, 5, 6. You can do any. You can see the beauty of how the progress are making. Every time we come up with the methods, we are eliminating the disadvantage of the previous methods. Again, it is solving for indeterminate structures. That is in the week number 10. By these times, you should be able to solve questions 1 on your assignment, questions 2 on your assignment, and question 3 on your assignments. So by these times you have made some progress and you have solved question 1, question 2, and question 3. Don't leave your assignment question at the last minute. It will be a lot of work for you and it will trigger some errors and so on. So make a weekly progress on your assignments so you can smoothly finish the assignments. Only remaining is two questions that you can finish, question 4 and question 5, that you can finish it off. And that's question 4 based on the moment distribution methods that I'm going to teach today. Now, these lectures will be introducing the moment distribution methods for indeterminate beam and frames. So as name suggested, this is the distribution of the moments. Remember that slope deflection methods, we have calculated the internal moments by calculating the rotations. If it is kinematic indeterminacy equal to 2, we calculate the rotations in this one. Now this moment distribution methods bypass this calculation of the rotations. You don't need to calculate the rotations in this moment distribution methods. You can avoid that one. It's very powerful methods, these slope deflection methods. And if you need more information, it can be found in the chapter number 12. Now, these slope moment distribution methods, I think last slope deflection methods was found in 1950s. I think almost 108 years ago. 108 years ago. Now, these moment distribution methods comes after slope deflection methods. Moment distribution methods comes after these ones. It comes in the 1930s. After 15 years, Professor Hardy Cross has invented these methods from Illinois University in USA, and we also can call these Hardy-Cross methods. If you don't want to say moment distribution methods, Hardy-Cross methods also it is known by Hardy-Cross methods as well. After these moment distribution methods introduced, these slope deflection methods was not so popular because it is eliminating the disadvantage of the slope deflection method, and it is faster as well. Now, let's introduce the moment distribution methods. Now, what is moment distribution methods? Idea of moment distribution methods is to calculate the internal moments without calculating those slope or displacements. You remember in the slope deflection methods, you calculate this theta value and we substitute back theta value in the slope deflection equation and we calculate the moments. And when we calculate the internal moment, that was balanced. You remember that at the particular point, I asked you to put the stop sign, and that stop signs is for that, okay, at particular joint, your internal moments would be either plus and negative, right? The value would be same, but then your answer would be same, meaning that sum of the moment at particular point was 0. That was the conditions that we satisfy, and we found that slope, and then we substitute the slope back into that equations. Now, this idea of moment distribution method is to distribute the unbalanced moment at the joint to adjacent member until equilibrium is achieved. So when you clamp your beams, you remember that the concept is still same. This is the part of the slope deflection methods, and moment distribution methods are the displacement methods. The group is same. The overall fundamentals is same. What is the fundamentals? That is a displacement methods. In the displacement methods, what we done? We clamp the internal joints, like we fix them to. And why you fix them? You know that you have kinematic indeterminacy. Kinematic indeterminacy. In the last lectures, we found the kinematic indeterminacy. How to find the kinematic indeterminacy? You can go back and check. So by clamping, so the concept is we want to make the structure determinant. We want to make sure that if there is any slope or displacements occurring internally, we want to make it 0. We say that there is no slope, there is no displacements. We will make all of them are 0. So we clamp them. So when you clamp all the internal moments, it will create the unbalanced moment. It will unbalance the moments. Now our structure is balanced. Original structure is balanced. All the internal sum of the moments are equal to 0. But when we clamp it, it becomes unbalanced. So now this method saying that when you unbalance them, you can distribute the moment until you get the equilibrium, because eventually we need the equilibrium in the structures. Our structures are not floating structures, or not, they are not in the space that is going from one end to another end. So for that case, your structure is a stable structures. It is a fixed structures. It is not floating. So they have a force equilibrium. They have moment equilibrium. Here we're going to use the moment equilibrium. So that's the concept. And this is done by iteration process until equilibrium moment is ready. And I will show you how to do that iterative process. Now, sign conventions, as you know, this is the displacement method. So your clockwise moment is positive. And if you remember the last week notes, that you can check it. And in that ones, I have described why the clockwise moment is positive. Now, there are a few concepts that I like to put forward here. The first concept is the stiffness. I hope you have heard about the word stiffness. Did you heard about the word stiffness? Stiffness. Everyone will understand the spring, right? You have in the physics, you will understand that you have a spring, one spring, and you attach with some mass to the spring. And when you attach this mass to the spring, it will goes down. Right, so you have suspensions. If you remember that in the car, the suspension also they have a stiffness. So the force that you are applying, that force by the mass is this one. So the stiffness is represented by the letter K, and that will divided force divided by how much displacement is occurring. So how much displacement that you are occurring. So that is the force over displacement. The unit is Newton per meters. So if I say that stiffness is 10 and stiffness is 20. So if I want to increase the stiffness, I need to reduce the deformations, as you can see that. So that's inversely proposed is the displacements, right? So the more it is a stiff, more the value that you're going to get is the more stiff you will get. So the materials, if you want to make a stiff, they should not deform against on that one. So that is the stiffness that you are getting. Now, in that case, you will have these these values. Now, equal to 4 EI on L. Right, now we have a beam. We don't have a spring, we have a beam. So in that case, beam is generally represented by the moment and rotations, like how much rotations you're going to create. Now, for example, let's forget about theta A. Let's say you want to rotate that beam by 1 radian or 2 radian or 3 radian. Let's say someone come and try to rotate that beam from the 1 end. How much moment do you require to rotate by 1? You remember in the last week we said that if you need the moment to rotate these ones for the materials that is made of, I is what is the cross sections moment of inertia against the moment over the length equal times by theta, because if it is 1, if it is 1 radian, then the moment required to create the 1 radian is 4 EI over L. The moments, if you require theta A moments instead of 1, and then you have multiplied by theta. So you can see M equal to K theta. You remember that, right? K equal to M over theta, like force over displacements. The stiffness is force over displacement, that is for spring, but for the beams we will replace the force by moment and replace the displacement by theta. So the same fundamentals hold for the beams, that the force in the beam is the moment, so it's a moment, and the displacement in the beam is the rotation, which is the theta. So if I want to say that M equal to K theta, and if I compare this equation M, then the K equal to 4 EI on L. Right, so I hope you understand that 4 EI over L, that is the stiffness in the beam, stiffness of the beam elements. If you take the one part of the beam and if you just hold the one end fix and you try to rotate the one end, how stiff is the material? How stiff is the beam? Is a 4 EI over L. So the stiffness is directly proportional to the Young modulus and I. The higher the Young modulus, more stronger. Like for examples, like the aluminium and steels. Aluminium has a Young modulus of 60 gigapascals. That is the E for aluminium. Steel has a 200 gigapascals of E. So you can look at that. Aluminiums, if you have an aluminium rod or something, you can bend it by hand. Like it is not strong because the Young modulus is smaller than the steels. So the steel one is more stronger. So the so directly proportional, as I said, the stiffness is directly proportional to Young modulus. Moment of inertia, I, it is directly proportional to stiffness. The higher the I, higher the stiffer value, but it's inversely proportional to the L, meaning that if you increase the length, your stiffness will go down. Right? So I hope it makes sense in terms of the beam. The three parameters that are required to find the stiffness of the beam, which is the E, I, and L. E and I directly contributed into the stiffness. The more E that you get, more stiffer material you get. More I, the moment of inertia that you get, more stiffer that you get. Length. If you increase the length, it will reduce the stiffness. You can see if you have longer bars, then it's easy to twist. So for that case, the higher the length, smaller the stiffness. And this case is when you have a fixed one at the end. When you have a pin or roller at the another end, then it becomes 3 EI over L, right? So that's and again, same concept. That's I want you to put forward that if you want to rotate this one by 1 radian, amount of moment required to rotate by 1 radian is given here. That is the moments. So 3 EI over L, that's the moments that you are getting. Now, so that's 3 EI over. So there are only two equations that you're going to come across. Stiffness when your far end is fixed, 4 EI over L, and stiffness when your far end is rollers, 3 EI over L. Okay. Now, stiffness factors. Any questions in the stiff concept? Now, the next terminology I like to introduce is the distribution factors. Now, distribution factors are used for calculating the how much distribution of the moments occurs in the particular member. Let's take one example. How does it work? So let's say there is a frame. Now this frame has a 3 members, member AD, member AB, and member AC, and they all connected at joint number A. Right? Everyone okay with me so far? That there are member AD, member AB, and member AC, and they are all connected at joint A. They are meeting at joint A. Now, when they meeting at the joint number A, you can say that this member has a stiffness of 1000 Newton per meters or something. This member AB has a stiffness of 4000 Newton per meters, and these members has a stiffness of 5000 Newton per meters. So there are, because stiffness, I think we can calculate using this equation here. So stiffness, you understand that K equal to and those ones. So the stiffness are there. K equal thousands, K equal to, so everyone understand the stiffness that it is given to you. Now someone asks you, can you please find the distribution factor for AB? How do we be able to find the distribution factors of AB? So let's say stiffness of that members, which is the 4000s, divided by total stiffness of the joint where your member AB is connected. Now what is the total stiffness of the joint number A? Total stiffness of the joint number A is 1000 plus 4000 plus 5000. So would be 10,000. That is the total stiffness at the joint number A. And divide 4000. That is the stiffness of the members that you want to find. So 4000 over 10,000 is 0.4. So the distribution factors of AB is 0.4. Similarly, what is the distribution factor of AC? Distribution factors of AC. Now the distribution factors of AC is distribution factors of AC equal to 0.5. How does it calculate? The stiffness of that members, particular members that you want to find, 5000 over the total stiffness at the joint where your member is connected, which is the point A, and total stiffness is 10,000. We already know, so it is 0.5. Someone asks you what is the distribution factors for member AD, then you would say the stiffness of that particular members divided by total stiffness. The total stiffness at joint number A is 10,000, so it's become 0.1. So I hope it is making sense. The one quick note here that you can check your answers whether it's going correct or not, that if you sum all the distribution factors, 0.4 plus 0.5 plus 0.1 is become 1. So that is become 1 at this particular joint. So if you sum all the distribution factors at this particular joint, you have 0.4, 0.5 and 0.1. So that is the one that you are getting. So that is the distribution factors for these cases. Now, if you have a I hope it is makes sense. Now, what is the meaning? I don't want you to just calculate distribution factor without understanding. Now, what is the distribution factors is meaning? If I say distribution factor is 0.4, what does it mean? What does it mean that let's say someone applying the moments, let's say someone applying 100 kilonewton meters moments here. Someone come here and bang at point A, 100 kilonewtons are applying this ones. Now this joint A don't wants to go or don't wants to rotate. It will give you the resistance against the 100 kilonewton meters, right? Because if someone go and start hammering or start rotating that joint A, there are three friends or three members that they are trying to support the joint A to not rotate. Now that brother AB or member AB will tell that I can help you to the 0.4 of these 100 kilonewtons. So it says that I can take 40 kilonewton meters. I cannot go more than that. My maximum resistance or my maximum help is coming from my side is 40 kilonewtons because his stiffness is 4000. That's fine. He take 40. Now this member AC is going to tell that I can take 0.5 of your moments. I can go up to 0.5. That is my capacity. I can take 50 kilonewton meters. I can help you joint number A, and AC is telling to the joint number A that don't worry about the 50 kilonewton meters. I will look after that. I have my stiffness 5000. I will use all my stiffness and I will provide the resistance to that 50 kilonewtons. AB is saying I can make it 40. This brother is very weak. AD is not too much strong. And it says that, sorry guys, I can take only 10 kilonewton meters. So that's the meaning of these distribution factors. When you see the distribution factors numbers, it is all the, keep in mind, if the distribution factor someone telling me is 1.1, something is wrong. You never get the distribution factors 1.1, 1.2. It should be always less than 1. It could be 0.1, 0.2, 0.3, 0.5 in that, or 0.25, 0.75, 0.65, 0.75, 0.74. That makes sense. So in the exams or in the assignments, if you are getting distribution factors 1.2, you don't know what you're doing because you don't understand the distribution factors. So if the students coming on the lectures listening this recording video, the recording of these lectures, they will not gonna make mistakes that said distribution factor is 2.5. No, it's not possible. OK, so I hope it makes sense. Now, if someone asks you to find the distribution factors at because look at this fixed supports. It's not nothing here. It is just a fix. So the distribution factors at the fixed joint is 0. Why? Because you can still do the calculations that stiffness of AB over infinity. This fixed support has an infinite stiffness, right? It's very strong. It does not deform. So it has a infinite stiffness. So infinite stiffness over this one. So something over infinity is 0. So the distribution factor of fixed support is 0. And the reason is that you have infinite stiffness at the fixed supports and you are dividing by infinity by some number divided by infinity. That makes it 0. So therefore it is fixed supports. It has an infinity. Now if you have pin or rollers, then your pin or roller has a 0 stiffness, right? It does not provide any resistance. There is not any stiffness. It is just free to rotate. So no stiffness, no resistance against the rotation. So the pin or roller has a 0 and this stiffness of AB over stiffness of AB. So you have 1. So distribution factors at pin or roller has a 1 and the distribution factors of the fixed support is 0. You don't need to remember that. You can imagine that the stiffness at the fixed support is quite stiff, quite strong. It's infinity. So K over infinity is equal to 0. And this K and pin or roller is 1. Any terminology I like to introduce, the third terminology that I like to introduce is the carryover factors. What is carryover factors? Now, carryover factors represent a fraction of moment that is carried over from initial end to the other end of the beam. So for examples, someone applying the moment here. Someone just come and try to rotate that point A by let's say 10 kilonewton meters. Someone come here and try to rotate point number A in this directions, and say that he's applying 10 kilonewton meters torque or moment that he's applying at 10. Now, because of the fixed support at here, it will create the reaction moment here, right? This joint will try to resist. You see, when you put the 10 kilonewtons and if you are fixing at other end and you try to rotate another end, it can have only 5 kilonewton meters of resistance. So the carryover, that the moment that will be carried to the other end is 5 kilonewton per meters. Does it make sense? That if you are applying 10 kilonewton meters at one end, let's say someone try to rotate that joint number A. When it's reached to the joint number B, it has become 5 kilonewton meters. That was the against the resistance or the reaction force that you are getting. So the carryover for the fixed support is you can see fixed support is 0.5. Now, when same beam, and I'm applying the same moment, 10 kilonewton meters, but here it is pin or rollers, which is not fixed. It is free to rotate, right? It does not have any resistance. You can look at my pen. If I let it go, then it's simply rotating. So there is a zero carryover. That becomes zero here. 10 kilonewton meters becomes zero here. When you carry to the other side, when there is a roller or pin, it's become zero. I hope it is makes sense. When you have fixed supports, the carryover for the fixed support is 0.5 and carryover for pin and roller is zero. So I hope it is clear. But when I take an examples, it will be more clear. All right, I'm not going through the procedures, but these examples that we're going to do it with our beam examples. OK, so I think so far I cover few details. That's I'm going to help you out here. Let me go back and take these examples from here. All right, so let's take these examples now. Let's put it here. OK, so that is all good. All right, so that is all good now. Let me open up my few things here, so we are on the same page. Yep, I'm just trying to open this note so we know where we are getting. All right, so that's all good now. Let's do it. The question here is to determine internal moments. Determine the internal moments. We need to determine the internal moments. Now, to calculate the internal moments, let me go back and get these figures clearly. We like to calculate the internal moments for these ones. Now, to calculate the internal moments, we're going to fix these ones and we're going to fix these ones, right? Because we have theta A equal to 0 here, theta B is not 0, theta C is not 0, and theta D equal to 0. So we have kinematic degree of indeterminacy equal to 2, which is theta A and which is theta B and theta C, right? Because that's 2. And now we make them 0 to make it determinant structures. Now step number 1, we calculate the fixed end moments. And you remember this is the displacement method. Displacement method does not like that force is coming on to that member. So for that case, we use displacement methods. Now, last week, we have this table. Let me show you the tables. Let me show you the tables. Last week we have week number sorry, week number 9. Week number 9, and in that ones we have these with these tables. Sorry, you need to go to week number 9 to get that table, please. Where is the tables? Oh, here you go. That is your tables that you have. So that is your tables. Let me get these tables, fix and moments tables for you. Copy and let's get these tables here. So this is the fix and moments tables. All right, so now this is a fix and moments tables. Now fix and moments at AB. Let me get back to this one and we copy again these ones. Copy and let's put it here. Paste. OK, now fix and moments of AB equal to 0 because there is no load coming on to the AB. BA equal to 0. Fix and moments of BC, or you can break it down these whole structures into various segments. Let me do that. So A and B and fix and moments of AB and fix and moments of BA. Then you can break it down here one more. And this one has a 20 kilonewton per meters. And this one is fix and moments of, this is B and C, CB, fix and moments of BC. And this one has a CD, fix and moments of CD, and fix and moments of this is DC, by the way, and this is CD, and the load is coming 250 kilonewton meters, 4 meters here, 4 meters here, 12 meters here. So in here, fix and moments of AB equal to 0 because there is no load. Fix and moments of BA equal to 0. Fix and moments of BC, and we need to make an assumptions. Clockwise moment is positive. Clockwise moment is positive. That is the assumptions that we make at the start. So this is anti-clockwise moment, so it's minus, and we need to find the same equations that match it here. So that is here WL square over 12. So minus WL square over 12, which is minus 20 kilonewton per meters times by 12 square over 12. This cancels, so 12 left, minus 240 kilonewton meters. And fix and moments of CB, same thing, but just the positive, so it will give me positive 240 kilonewton meters. And fix and moments of CD, and we can find a similar one, which is here, PL on 8. Minus PL on 8, which is minus 240 kilonewtons. Length is 8 meters over 8, 8 cancels, minus 240 kilonewton meters. And fix and moments of CDC is same, but it's positive 240 kilonewton meters. Okay, so we done this one. We done this process, I think, in the slope deflection method. Same things, nothing new so far. We break it down the whole structures into the segments, and then we find the fix and moments using the tables that we have used it last week. Now that is a step number 1. All times that you can calculate the fix and moment. Step number 2, we can calculate the stiffness. We can calculate the stiffness for your members. Now to calculate the stiffness, I think there are only two equations. Let me go back and take you through that two equations. I don't want you to just say that look at the lecture notes by yourself. I will take you directly to there, which is on this page. And if I just quickly get it, so there are only two equations, that is here. So edit, copy. So this is the information for stiffness, and these informations are given here for stiffness. So there are two equations. When your far end is fixed, you have 4 EI over L, and where your far end is pin or rollers, you have these equations. Now let me go back in here and let's get the questions as well. Let's get the questions as well. Question is here. Let's get these questions. All right, so this is your questions, and these are the equations. So stiffness at, so these are all your fixed. These are all your fixed. This is already fixed. This is already fixed. We can't touch it. So far end is fixed. So stiffness of AB equal to 4 EI on L. So 4 EI on 12 meters equal to 0.33 EI. Stiffness of BA equal to, if you look at the BA, you need to look at the far end. A is fixed. So 4 EI on 12, 4 EI on L. So 12, it is 0.33 EI. KBC. Now the next one is KBC. KBC, you need to look at the C. C is fixed. 4 EI on L, 4 EI on 12. So 0.33 EI. KCB, again 4 EI on 12. Look at the B. B is fixed. So you have 0.33 EI. And stiffness of CD equal to, look at the D. D is fixed. So 4 EI on L, which is 4 EI on 8, which gives me 0.5 EI. And KDC, I think I made a mistake. I think our stiffness at AB would be 0 because it's a fixed supports. BA would be so this one stiffness, fixed stiffness would be your, this is A to B. B is fixed, but this one is fixed, so 0. BA is this one's. BC is this one. CB is okay. CD is okay, but CDC equal to 0 stiffness because this fixed support is quite strong. It's infinity, so that's all good. So I hope you understand. Stiffness is found. And now number 3, we're going to find the distribution factor. Distribution factor. Now to calculate the distribution factors, we have distribution factors of AB equal to KAB on KAB plus, I think that is a infinitive, and KAB. So the stiffness of KAB over infinitive, which makes it 0 because the fixed supports. So fixed supports is fixed end. It is 0. Distribution factor of BA. So the distribution factors of BA here, we need to find BA. So there are joint B. So KBA over KBA plus KBC, because you can look at these figures that joint B has a 2 members, BA and BC. So BA and BC. Now stiffness of BA is 0.33 EI. Stiffness of BA 0.33 EI plus KBC. KBC is 0.33 EI. 0.33 EI. So 0.33 EI over 0.66 EI. EI cancels, you get 0.5. Distribution factors, DF. Distribution factors of BA done. Now we can calculate BC. Distribution factor BC equal to stiffness of BC over stiffness of BA plus stiffness of BC. BC has a stiffness of 0.33 EI. BA has 0.33 EI plus 0.33 EI. So you get 0.33 EI over 0.66 EI. You get 0.5. Distribution factors of BC done. CB. CB equal to KCB, and CB is here. CB is here. EI over 0.83 EI, which gives me and by the way, look at these ones. Is a 1, right? If you sum that BA and BC, you sum BA and BC would be 1. If you sum CB and CD, it would be 1 as well. So that one would be CB would be 0.4. And if I want to calculate distribution factors of CD, straight away I can put 0.4 equal to 0.6, or you can calculate long way like KCD on KCB plus KCD equal to 0.5 EI on 0.83 EI equal to 0.6, and you can have it. So you can look at that. All distribution factors are less than 1.0. Therefore it is okay. All distribution factors are less than 1.0. Therefore it is okay. At joints, distribution factors are sum as 1.0. So yeah, we check it. Therefore it is okay. Right. So we make 2 checks saying that distribution factor is less than 1.0. Check is done. And it all looks okay. Distribution at joints, all the distribution factors are summed to 1, and there we check both of them. Any questions so far in calculating the stiffness, in calculating the distribution? One more distribution factor of DC, and that would be 0 because fix because of the fix end. And I can make a one more check. Check number 1, check number 2, check number 3. Fix end distribution factors equal to 0, and pin or roller distribution factors are 1, right? And we make these all checks. Therefore it is okay. So we make 3 checks and saying that all these are okay. Now the last 4 steps is to build the tables. We need to build the iterative tables. Now I need the full attention from the students to do this iterative process. I need the full attention, meaning that if you distracted by somehow, then you will not be able to get all this. There are big numbers and those numbers are moving from one end to another end. So you make sure that you have full attention. If you have a notebooks and if you are doing in the final exams, or you have doing in the workshop example or in your assignment questions, you need to start this table from the beginning. Meaning that if you have a book, if you are working on the notebooks or in the answer book or something on the assignment question, and you are on the halfway through the page by the calculation of fixed and moment, stiffness and distribution factors, leave this space empty. You start these tables from the beginning of the page, just from the top of the new page. Does everyone make sense what I'm trying to say? These tables that we're going to develop, I would suggest. So now let's build the tables with you. Now, the tables that we're going to build is going to be like that. Okay, I will work with you now. Now, first of all, oh, let me put that figures, by the way, the questions that we are solving. Copy and let's put it here. So we have these questions. We want to keep it in front of us. Now, let's say on the left side, you write joints. Joint number A, put a round, and joint number B, joint number C, joint number D. Everyone okay? This is given here already. You just need to copy it. Joints A with a round, B with a round, C with a round, and some space in between. Okay, everyone okay with that one? Once you do this ones, you can use the ruler or something to draw the straight line as much as possible, the straight line. If your hands are wobbly like me and you can't draw the straight line, use the rulers to draw the straight lines. Keep the rulers handy and use the rulers to draw the straight line. Right? So from that particular joint, from the middles, don't draw something on the left, something on the right. From exactly in the middles, approximately in the middles, draw the line coming from that joint. So far, so good. Once you write the joints, you can write the members. From the left side, from the right side of that line, write AB, write BA. It is like this: AB, BA, BC, BC, and CB, and CD and DC. So far, so good. I have done nothing wrong, nothing I have done new. I just have that figure in front of me, and from that figures, I have drawn these members. All right. After that, you write distribution factors, or you can write big one and draw the horizontal line after distribution factors. And probably let's put the distribution factors in the green. And we calculate distribution factor for AB, and distribution factor for AB was 0, and that is fixed support. So distribution factors for here is 0 and it's matching. Distribution factor for BA, distribution factor for BA is 0.5 and BC is 0.5. So BA is 0.5 and BC is 0.5. Distribution factor for CB, let's go back, check. CB has 0.4 and CD has 0.6. 0.4 and 0.6, and DC has 0. DC has 0 because it is a fixed support. DC has 0. So I hope it is making sense that you have EB 0, and if you sum this one here, BE 0.5 plus 0.5 is 1, 0.4 plus 0.6 is 1. So here also you can make a quick check, making sure that when you copy those distribution factors from your notebooks, you don't copy something that triggers some error. They are not adding up to 1. So here you can also have make one quick check that they are adding it up 1. Now, then you can have fixed and moments. Fixed and moments, we can calculate AB has a fixed and moments of 0. I think we can go back all the way up. Fixed and moments AB and BA is 0. So that's fine. AB has a fixed and moment 0. BA has a fixed and moments of 0. BC has a fixed and moments of minus 240, positive 240. We are not writing units because otherwise it will get too conjuncted. So minus 240 for BC, CB has 240. Then CD has minus 250 and positive 250. CD has minus 250 and positive 250. Right? So far, so good. Right, any questions or any get, so in case if you miss any details where this number coming from, you can go back to this recording and pause it and understand where this numbers coming from. So you know where these numbers are flowing, where those numbers are coming. All right. All right, so this is all good. Now we will write balance 1. Now you can look at this joint number B. Let's start with joint number B. Now joint number B, on the left side it has a 0 moment, and on the right side it has minus 240. Can you see these fixed end moments that are listed here? That it has 0 moment on the BA and it has a BC has a minus 240. So if I add up these two moments, I would have minus 240 kilonewton meters moments. And you know the rules here. All sum of the moment at the joint would be 0. This is not happening in our beams. Why? Because you can look at that, because at the beam, when you clamp it, you have disturbed the beam and it has extra 240 kilonewton meters extra moments. No, we can't handle that moments. We need 0. So let's make it 0. Who wants stopping us? So if I add 240 in this one, I can make it that one 0. Everyone okay with me? No one's stopping us to make it 0. So it's at the moment there are minus 240 kilonewton meters extra moment sitting at point number B, at the joint number B. And our rule saying that sum of the moment at joint number B would be 0. And it's not summing up to 0. So let's make it 0. I would put 240, positive 240 here at joint number B. So when I put positive 240 at joint number B, you know that BA can handle 50% of 240. You know the distribution factors theory. Someone coming and banging on the point B with 240 kilonewton meters positive to make it equilibrium, then the joint B need to resist somehow. And the joint B going to take the help from BA and BC. And the BA said that I will take 50% of that one. So 240 times 0.5. It's give me 120 positive, and I will take BC said I will take 50% of S1 as well. So 120. Now, if you sum them all up, then it becomes 0. You can look at the word balance. 0 minus 240 plus 120 plus 120, it becomes 0. Excellent. That's what we wanted. This is all good. Joint B is the joint C. How much moments you have extra there? At CB, you have 240 and you have 250. So minus 10 is an extra moments, which are unbalanced moment is minus 10 kilonewton meters. Now, to make it balance, I would make it minus 10 to plus 10. Because if I add plus 10 into the 10 minus 10, it make it 0. It become balanced. So let's say you are going to make it 10 kilonewtons moments here. Again, the concept is same. CB says that I will take 40% of 10. 0.4 will going to take from that one. So plus 10 times 0.4 equal to 4. So this guy can take 4. And the remaining, which is 10 times 0.6 equal to 6. So that will taken by 6. I hope it makes sense. This guy is by itself. So 0 times 0 is 0 and 250 times 0 is 0. So you can look at these balance steps. Look at the balance steps. Balance steps saying that your joint would be all balanced, right? And we make that balance. Now draw a line after balance. Then we write carry over 1. Now for carry over 1, we have sitting 120 kilonewtons here. You look at this one. This is 120 kilonewton. If it goes on the other side, it becomes 60 because it's a fixed end. So the carryover would be 120 times 0.5. So it would be 60. 0 times 0.5 is 0. These all internal are fixed. These are fixed. These are fixed. So 120 becomes 60 multiplied by 0.5. You remember the theory for this one, 2. And carry over 0 times 0.5 is 0. 6 times 0.5 is 3. Right? So that is all good. We will continue that one. And now we're going to write balance 2. And in that balance 2, again, we come back at joint number B. You have 2, 0 plus 2. So 0 plus 2 is positive 2, and we want to make it, this is plus 2. If I make minus 2, then it becomes 0 2. From minus 2, 0.5 times and 0.5 times because distribution factor. So you with me that I can write minus 1 here. Positive 2, we need minus 2 to make it positive 2 to 0. And then we multiply by distribution factors with 0.5 with minus 2, 0.01. So 60. Here at joint C, we have 60 plus 0, which is positive 60. Positive 60 turns to negative 60 because we need to make it 0. And then times by 0.4. So if I multiply by 0.4, you will get minus 24 and you will get minus 36 because you multiply by 0.6. So you get minus 24 minus 36. And 60 times 0 is 0. 3 times 0 is 0. Right? Yeah, it is quite little bit require attention and your practice as well. So you need to do it a couple of times to get over these ones. So balance 2 is done. Now again, we do carry over 2. Same rules, 0.5 minus stays minus. So minus 1 times this one minus 0.5, 0. Here minus 24 times 12, minus 12, minus 0.5, minus 1 times that. 36 become minus 18, that 0 becomes 0. Right, balance 3. Now, we need to know where we're going to stop it, right? You can't continue like this, balance, carry over, balance, carry over, balance, carry over, and so on. Right, so how are you going to, how do you going to decide whether it's going to be stop or not stop? So let's do this check. So here you have minus 12 as an unbalanced moment. So let's forget about the minus or positive. Let's say there is a 12 year balance moment. When we started, it has a 240 because when you remember this one here, we started at the start fixed moments, it was 240. Initial moment was 240, and then we come back to the 12. So 12 over 240 and times by 100 to calculate the error percentage. So I will calculate 12 over 240, you get, and times by 100, you get 5. So which is less than or equal to 5%. So therefore it is okay. We can stop it. But here, let's check the another one, 0.5. That is 1 here, and here we started with 10. 10. So times by 100 equal to 0.5 times 100 divided by 10, you get 5%. 5%. So I think we still, it is not okay. We might need to do more interactions. Probably we would like to keep it at 1%. Let's say we can stop it at 1%. The more interactions you're going to do it, the accurate results you will get. So our target would be, let's say 1%. So let's continue that. Now the balance here, minus 12. So we make it minus 12 to positive 12 and multiply by 0.5. So positive 6 and positive. So if you sum this one all, it becomes 0. Minus 0.5 become positive 0.5. Minus 0.5 become positive 0.5. And 0.5 times 0.4, you get 0.2, which is positive 0.2, and 0.3, 0.5 times 6. And minus 18 times 0 is 0, minus 0.5 is 0. So balance 3 is done. Carry over 3. So that's get 3. That's get 0. Multiply by 0.5, by the way. 3, 0.1, 0.15, 0. Right. Now let's check again. So there is a 0.1 over 240 times by 100. So 0.1 over 240 times by 100, you get 0.04%, which is less than 1%. So therefore it is okay. We can stop it. But we can check the other joints as well. We need to check all the joints. 3, over 10, right? 3 over 10 times 100. So 3 over 10 times 100, you get 30%, which is quite high, which is greater than 1% or 5%. So we need to continue. So balance 4. Therefore, I tell you to start at the first page. You remember that you need to put this one, all these ones. So 3 times 0 is 0. There is a distribution factors. Positive 0.1 become negative 0.1, and negative 0.1 times 0.5, you get 0.05 minus and 0.05. 3 become minus 3, and minus 3 times 0.5. 3 times 0.5, you get minus 1.2. And you get minus 1.8, and that is 0. So that is all good. Now we can carry over. That would be 0.05 times 0.5. You get minus 0.025. You get this one 0. 1.2 times 0.5. You get minus 0.6. 0.5 times 0.5. You get minus 0.025. So 0 and 1.8 times 0.5, you get 0.9. Let's check. This is carry over 4. So this one is okay. 0.6 over 240 times by 100. 0.6 over 240 times by 100. You get 0.25%. Very small. That is okay, which is less than 1%. That is okay. This one here, 0.025 divided by 10 times by 100. So 0.25. So 0.025 over 10 times by 100. So you get about 0.25. So that is okay now, 1%. So both are very small numbers. Now you can feel it that all getting very small. And you never stop at carryover. Listen to me carefully. That some students will just check the error and stop it, because carryover is not your moments are not balanced. So you never ever stop at carryover. It's wrong. If someone stop at carryover, it is wrong. I repeat again, when you feel that you want to stop, you check the error and you say that, okay, I have decided to stop it. Then you do one more step and stop it at balance, because the balance where you going to take all the moments are 0. So this one would be 0.6 become positive 0.6, and positive 0.6 times 0.5 would be positive 0.3, positive 0.3. 0.025 minus become positive times by 0.4, which becomes 0.01, and you get 0.015, and that is 0. So that is your final balance. You stop it here, you check it, so that is all good, and then you're going to sum the moments. You're going to sum the moments. So what you're going to sum? That you start from here, 0 plus 0 plus 60 plus 0. So 60, I'm just putting in my calculator, 60 minus 0.5, 60 minus 0.5 plus 3 minus 0.025, you got 62.48. Let's say take 2 decimal places. Then you take fixed moments from here, 0 plus 120, 120 plus minus 0.1. Sorry, it is always messy. Plus 6 minus 0.05 plus 0.3. You get 125.25. Do it again. Minus 240 plus 120. 120 plus 2 minus 1. Minus 12 plus 6. 12 plus 6 plus 0.1 plus 0.1 minus 0.05 minus 0.6 plus 0.3 you get something I screwed up. Let's type it again. Minus 240 plus 120 plus 2 minus 1 minus 12 plus 6 plus 0.1 minus 0.05 minus 0.6 plus 0.3. Yep, that's finally good. Minus 125. Stop it here. Look at this. These are the same numbers at the joint. Smiley face. I'm happy. So you can see I screwed up something. I got a different answer. I did it again and looked like I'm doing correct because at joint B, they are both same number, equal and opposite. Joint number C. So 240 plus these ones, I will plus them. 240 plus 4 plus 60 minus 24 minus 0.5 plus 2 plus 0.2 plus 3 minus 1.2 minus 0.025 plus 0.01. You get 281.49. Let's do the two decimal places. 281.49. Let's work two decimal places. So then you start here minus 250 and you go all the way down 6 minus 36 plus 0.3 minus 1.8 plus 0.015. You get minus 2. I'm very happy that my numbers are coming, shaping it up. And finally, 250 plus 3 minus 18 plus 0.15 minus 0.9. You get 234.25. So that is your answer, n moments. Let me go back and put it these details in our figures. So positive is a clockwise is a clockwise is positive. So this one is clockwise because it is positive kilonewton meters. This one clockwise 125.25 kilonewton meters. This is anti-clockwise. This one's 125.25 kilonewton meters. This is clockwise, so 281.49 kilonewton meters. Anti-clockwise 281.49 kilonewton meters. This one clockwise 234.25 kilonewton meters. That is your final answers. I think once you know these ones, you remember that last week, you can just do this reaction reaction AB or something like that, reaction BA, and the moment is 62.48 kilonewton meters, 12 meters here, and the moment here 125.25 kilonewtons. And from that, you can apply joint A, joint B, and you can find the reaction. Remember that in the slope deflection methods. So that's what you can. So I have done nothing new. I just get all these details. I can show it to you quickly again. So this is the plain Excels, and I go here and I take these ones, copy, and I put it here. So that is our question. So I put it on this one corner. Then I go here and I will like. So here we can compare these ones, these two. Okay, so far so good. You can see it as was nice and clear. Now, let's start here. So here you can put joints, and from that joints you can have let's start with members and the joints. So members would be, we can have it AB, and we're going to leave the one gap here and we put BA. Let me do this way, and BC. And we're going to leave one gap here, CB and CD. I'm sure you know what I'm doing. I'm just typing these ones. And DC. And let's say here we will have a joint A, we have joint B, and here we have joint C, and here we have joint A, joint D, right? We can draw the line. Let's put the line here. So it looks like exactly what we are doing. Let's put the line. Let's put the line here. And C, B, and in between let's put the line here. The line here, and here we can put the line here. And yeah, that's it. I think this one is not required. We have joint number A. All right, so that looks good. It really needed. As it looks, yeah, that is better. We don't need these ones, extra lines. So joint B, joint C, and joint D. All right, so that's, I hope you can prepare these kind of things. Then we can put distribution factors, and distribution factors was 0, then 0.5, you have 0.5, you have 0.4, 0.6, and you have 0. And we like to put this one in the center, and let's put it yellow so we can use them again and again. And after distribution factors, we like to draw the line. That's when we done it, right? Now fixed end moments, let's put fixed end moments here. And fixed end moment was 0. We have 0, minus 240, and 240, and minus 250, and positive 250, right? So I hope it is, put it in the middle. And then we will have balance 1. Okay, now at the balance, as you know, what we done, we put the minus sign in front of that, and sum is 2. You with me? We put the minus sign in front of that because we want to change it to the 250 into positive 250, and we want to have it sum of these ones times by the distribution factor. Positive 120, you look at that, positive 120, same thing, equal to minus sign, sum, these two, times by distribution factor. Then positive 120, that is good, positive 120. Same thing here, equal to minus sign, sum these two, times by distribution factor. And equal to minus sign, sum these ones, times by distribution factor. And equal to minus sign, sum this one, times by distribution factor. Oops, sorry. Equal to minus sum this times by distribution factor. Right? That is the balance. And after balance, we draw the line. Let's make it in the center, and after balance, we draw the line. Then we do carry over 1. Let's make it more space for that one. In the carryover, if you remember that, we need to multiply these ones equal to these ones times by 0.5 equal to this one's times 0.5. right? This one carry here. So this one times 0.5 equal to this one times 0.5 and equal to this one times 0.5 and equal to this one times 0.5. Right, the magic will occur now that if you want to repeat, what you can do it, you select this and you do it like this. But I think there is a problem here because you can look at this. Distribution factors need to be logged because this is not correct. So let me go back and we're going to log these distribution factors, selecting, pressing F4, and it will log. Otherwise, you can put the dollar signs. Otherwise, you can put the dollar signs like this, typing, or you can select and press F4 in the keyboard. That will lock it. So press F4, lock it. Press F4, lock it. Because we don't want to change this. It will be, so this one lock, this one lock, this one lock, this one lock, this one lock. Look at this magic. Carry over to minus 0.5. Look at this, carry over to minus 0.5, 0, minus 12, bang. You can do as many as you want. Look at this. Now students ask me, and we can, what happens here? Why there are balance 1, balance 2, balance is not changing. That's anyway, that's all good. So Control Z and balance 3, 0.03. Yeah, we can stop it at balance 3. I think this one is not changing, balance 1. That's okay. Now student asked me how to check the errors. Error would be checked at the carryover. So if you want to check the error, what you can do it, you can do sum of these two divided by sum of these two times by 100. So that is minus 0.83. We don't need to ignore the minus sign, and this is how you check. You can sum what is the unbalance that you got, and you can check all these ones by doing this. Carry over, we don't need to worry. So there is a 600 here error. This one here minus 0.83. We don't need to check it at balance. You have, let me check. Oh, we need to lock it, I think, by the way. Can we lock this one? No. Control Z, so we need to lock it. Or you can put positive 240. So that's perfect. And let's see if it is working. Yep, it looks like working. Balance, we don't need to check. Balance, we don't need to check. And this one. So you can see the error. You can check this one, divide by these ones. These ones divide by these ones. These ones divide by these ones. These ones divide by these ones. Now, if you want to check this error for these joints as well, I think if I do it this one, does it work? No, it does not work. We need to do it manually. Equal to sum carry over of these ones divided by sum. We need to carry over these two, but we need to fix this one. We can't change that. So minus 6. So you can see balance, we don't need it. Balance, we don't need it. This one, we don't need it. So error is 0.25, 0.25. Now, finally, we need to sum the moment. So equal to sum to fix end moments. And you can just drag it like this. Look at this. These two are same, perfect. These two are same, which is perfect. Does it make sense? I think these ones give you the more. You watch me. Okay, initial moments. First, you get the initial moment, initial IM, initial moment. What was the initial moments here? You can see here. The initial moment is 0 minus 240. And that is minus 240. We just take it positive. We don't need to worry about minus sign or anything for calculating the error. Just take it 240 as the initial moment. Now, when you have a carry over 1, you have unbalanced moment of 2. So you have carry over 1 has an unbalanced moment of 2, right? So how do we calculate the error percentage? Percentage of error. That's the equations. Percentage of the error. You take the carryover, whatever the carryover where you want to calculate over the initial moment. Now carryover moment was 2 at particular steps that carry over 1 or 2 or wherever you want to calculate the error. Over the initial moment is 240. And by the way, times by 100 to calculate the percentage. Times by 100 to calculate the percentage. So then you have times by 100. So you have 2 over 240 times by 100. You get 0.8 percentage of error at the carryover 1 at the joint number B. Now, if you want to carry over 1 at joint number C, you again have a carryover over initial moment times by the 100 percentage. So carryover at this particular point is 60 over initial moment 240 times by 100. So that will give you 60 over 240 times by 100. You get 25 percentage, which is greater than 1%. So we continue. We're going to come back here, carry over to minus 12. So again, we can just erase these ones, carry over to at point number B, right? And let me erase these ones as well. So for that case, the percentage would be here you have carry over to, you have minus 12. We don't take it minus 12. We just take it just a positive 12 and put it 12 here. 12 over 240 times by 100, you get 5%. So in here, we got 5%. Carry over to at point number C. At point number C. So carry over at point number C would be minus 0.5. Let's take it positive 5. So minus 0.5. Just take it positive 0.5, by the way. So 0.5 over 240 divided by times by 100. So you get 0.21. So you get 0.21. So you stop when both errors will get less than 1%. Here, one of these is 5%, so you need to continue carry over 3. For carry over 3, you have 0.1. So let's erase this. Carry over 3 has a 0.1. It has a 0.1. So 0.1 over 240 times by 100, you get 0.04, which is less than 1%, which is okay. Now let's do the point C carry over, and it has a 3 over. Here I make a mistake. Here should be 10. Here it should be 10 because this is at point C. So just make it correction. Here is 10 because you have 10 here. So here 3 over 10 times by 100, you get here. All right, so here I hope you can see. All right, so here you go. Let's get the laser pointer. I think we've done all of this. We've done these examples. All right, so being with concentric moment, I think I will brief you about these ones. There is not much difference on these ones. Keep in mind there are 2 EI, 3 EI, and 3 EI, and there is a concentric moment. These are pin and rollers. They are not fixed supports. That's the difference from the previous ones. Now, you can calculate the stiffness. I think you know how to calculate the stiffness. 3 EI on L. Now on here, your EI would be changed to 2 EI. You can see that 3 EI on L and 3. Why is 3? Because you can see this far end is a pin, so you can't use 4 EI over L. You need to use 3 EI over L and change to 2 EI, and you get stiffness 0.75. Stiffness of BC 4 EI over, because all internal supports are fixed. So 4 EI over L, but EI changed to 3 EI. So that is 3 EI over length 8 meters. CD, your far end is roller, so 3 EI over L. So 3 times 3 EI over L. So that's here. Distribution factors, as you know, pin and rollers has a distribution factor of 1. If it is fixed supports, you have distribution factor of 0. So that straight away you put AB and DC equal to 1. Distribution factor for BA, stiffness of BA, or sum of this one. So you can just have substitute this value and these values, you will get 0.33 and 1 minus this one. As you know, for at point gamma B, it is 1. So you can just straight away minus that. CB, here CB to C to D, stiffness divided by total stiffness, and again it's sum to this one. Fixed and moments easy. You can fix this one, and using our tables, you can calculate the fixed and moments for this one. So stiffness, distribution factors, and fixed and moments. That's 3 things you need to calculate before you go on to that table. Now you know this. You put the joints, then you put the members, and then you put the distribution factors, like the distribution factors that you calculated. Then when you come here, you need to distribute these. You remember that we have carryover and balance steps, but here you need to distribute this 50 kilonewton meters. It's already there. It's nothing we have disturbed or anything. It is already there. So we need to start with this one. So 50 times this one, so it'll give you this one. 50 times this one, it will give you this ones. And then you do carryover, like 50% carryover here, carryover is 0, and so on. And then you put the fixed and moments that you have, and then you sum them all. Like if you want to distribute 15, take away 26.16, which would be minus 15, take away 26.67, which would be minus 11.67, and you multiply 11 by these ones, multiply by minus 11 by these ones, you will get these ones. You sum all these ones, which is 16.67 plus 26.67 minus 40, you get 3.34 positive, and then you might make it minus 3.34 times by this ones, you will get this, and times by this ones, you will get this. And you continue this process, and when the error get very small, you sum them all up. Right, so that is all fixed and moments that you can put. Clockwise is positive. If you have beam with overhang, you can change this one to the concentric moments, 40 times 3, 120 kilonewtons. You can see we put 120 kilonewtons, and the same procedure: stiffness, distribution factors, and fixed and moments. And joints moments, we can start. This one's 50, we can change it. 120, we change it here, and then carry over, fixed and moment, distributions, and then carry over, and so on. Again, these ones, if you have these support be settled by 10 millimeters with these moments, you can do this. Again, stiffness and settlement. I think there is a fixed and moment for settlement. Here you go. There you go. This is settlements, fixed and moments that you can take into account the fixed and moment for settlement. So don't worry about the settlement. It is taken into account these fixed and moments calculations. And again, these procedures would be boring for you. It is same thing. Frame, you can do it with the frame as well, like stiffness, distribution factors, friction moments, nothing, same thing. And you can just build your tables for the friction moments, and you can carry out these calculations. But in the workshops, I think we're going to do it in the more great details in the 2 hours, because we're not going to cover the theory. So the two equations to calculate stiffness: 4 EI over L, where the fixed end is when the far end is fixed, far end is spinner roller, you have 3 EI over L. Distribution factor, stiffness over total stiffness, KI over is 0.5. So I think that's